First of all, it's great to be part of this exciting program in astrobiology. As you just heard now, what I want to talk about is how chemistry became biology, the origin of life question, a fascinating question. And maybe a little bit of my personal history will show maybe part of the problem as well. For the first few decades of my career, I worked in chemical reactivity, why some reactions are fast, other reactions are slow, why is that? And biology, that's another discipline. I'm a chemist, I don't deal with biological problems. Until some 20 years ago, it suddenly dawned on me that the biggest problem in chemical reactivity was biology. How did dead stuff become living stuff? And it's strange that chemists as a group don't really go into that area. It's as if it's another discipline. But I thought this is it's the interesting chemical problem. The second point I want to make is that actually, apart from being relevant in itself, how did life on Earth emerge from non-life? One can ask, what's the relevance of this to astrobiology? And I think there is an important element there as well. Because if we're looking, an even more fascinating question maybe than how did life on Earth emerge is there life out there? Are we alone? And we're obviously, that's part of astrobiology, trying to explore this in different ways. Seeking biosignatures, SETI, and so on. But it will help a lot in trying to figure this out if we understand the process as it occurred here, to understand better what is life, because we're still struggling with that question basically. So if we understand better what is life by studying how it emerged on Earth, then we have maybe we'll have a better means of probing the possibility, the likelihood of life elsewhere out there, and to finally get an answer to the "are we alone" question. Okay, so these are the topics I want to cover. I'm not going to, I don't want to go through this list. It's for the record, really, just so one has a list of the issues that I want to discuss, and we'll see what we can get through. And there is the question posed directly: how did a molecular system of some kind of molecular weight, something like 10 to the minus 21 grams, become an assembly of 10 to the minus 12 grams? Now, that's 9 orders of magnitude. 9 orders of magnitude, maybe that doesn't sound too significant, but that's equivalent to a pinch of salt being transformed into a herd of several hundred elephants. How did that process of complexification come about? We don't know. The physicists don't know, the chemists don't know, and the biologists don't know. So this is the first very strange thing. And the second thing, it's not just that we ended up with this complex system, but this complex system has unusual properties, like having an agenda, acting on its own behalf. How did dead stuff suddenly complexify and start to look after itself and its interest? Very strange. So this emergence of life from non-life is a big, big problem. And what I'm essentially saying is we're still lacking a physical chemistry theory of life. Biology is a subject that is still looking for its theoretical pillars to hold it up, and we're not there yet. So what I want to try and do with you now is to explore with you how we might get there, okay? Just one point, which I'll be mentioning more as we go along. the probability of the spontaneous formation of a bacterium from its components that had just happened by chance has been estimated by a well-known biologist, Harold Morowitz, as 1 in 10 to the 100 billion. Now, that is such a crazily unlikely, that number is so big that we can't even imagine how big it is, and we'll see a little bit more about the meaning of that number further along. So, the origin of life question, it's actually several questions. We can ask different facets of the question. We can ask, when did this happen? That's the historical question. Can we specify a time frame? Where did it happen? What location on the early Earth? One can call that a geochemical problem. How did it happen? What chemical path was taken? We can think of that as a chemical problem. And then there's the why question, which some people will say, why? What do you mean, why did life emerge? Are you allowed to ask questions like that? The answer is yes. Luckily, Newton asked, why do apples fall? And as a result of answering that question, physics made a lot of progress. So why did life emerge is a very important question, which I will try to say something about as well. So is there a physical basis for the process, something that drove non-living to become living? And then, are we alone? Will it be easy or hard for life to emerge? And I will just mention here as an aside, you people probably know more about this than I do, from the Kepler space mission. There could be as many as 40 billion Earth-sized planets in habitable zones in our galaxy. So just on a statistical basis, one would have to say there's a reasonable chance, a good chance, I don't want to specify that too precisely, that there must be, it's very likely that there is some kind of life elsewhere out there, and we are not alone. But that, as I say, is speculation at this point. Panspermia, one has to mention that just to clear the decks, get it out of the way, and then get down to the serious stuff. Panspermia, the idea that life arrived from outer space somehow. It was first suggested by a Swedish chemist, Arrhenius, at the beginning of the 20th century, with the idea that spores driven by light from another sun brought life to our planet. That's not really considered serious now. There's another suggestion that I wouldn't have even brought up if it wasn't suggested by two great scientists, Francis Crick of Watson and Crick fame, and Leslie Orgel, one of the leading figures in prebiotic chemistry, and they talked about directed panspermia, which is the deliberate seeding of our Earth by other civilizations. I think the fact that these two great scientists, Orgel backtracked on this subsequently, but that they suggested shows how working too hard on the origin of life problem can frazzle your brain and get you all confused. And anyway, today, of course, we don't believe that. And more importantly, that even if you believe in panspermia, it doesn't solve the basic problem. It just switches the problem from one location to another. So if life came from somewhere else, how did it start somewhere else? Okay. And in any case, as I will try and show you in the course of this talk, there's considerable evidence that life did begin on Earth from abiotic beginnings. Okay, how do chemistry and biology relate to one another? Let me start by saying basic things that you all know. Stuff is made of molecules, water, methane, sodium chloride, a fancy molecule there, fullerene, 60 carbons in a football. Molecules. Stuff is made of molecules. And living things are also made of molecules, but different molecules. Amino acids, sugars, fatty acids, nucleic acids. But of course, the molecules of life are not in themselves alive, okay? The riddle is not whether molecules are alive, but how the organization of these molecules, the self-assembly of them, leads to the properties that we classify as life. So let's start by going through the various questions and seeing where we are with it all. The first one, when? The historical question. Maybe it'll help us with the other ones. We all know, certainly this group here, that the Earth is about 4.5 billion years old, and if we put that on a 12-hour clock, life began roughly at the 12-hour clock starting at midday and ending at midnight. Life started at about 2 in the afternoon. Not too, beginning well into that period, but not too far along. 3.5 to 3.8 billion years ago. And it really couldn't have started much earlier because in that initial period, again, you people have probably been hearing this and will be hearing more during the conference. The Earth was subjected to heavy bombardment by meteorites, asteroids, giant impacts, which would have made the conditions impossible for life. That's the current view. So in that sense, there's almost a hint there that life started fairly early on Earth from the time that it could have. That's quite significant in itself. But that life, of course, was very simple life. We're talking about prokaryotic life, bacteria. And it took quite a while before what we think of life now, plants and animals, came about, and that was about at 10 at night already. That's 600 million years ago. And we people, when did we appear on this clock? At 2 seconds to midnight. That's also significant in the sense that we haven't really proved our robustness and our ability to stick around for a long time like other life forms. So one has to wonder about that. But that's already another question. Okay, how do we know? How can we time things? Radioactive dating, certain heavy elements are radioactive and they decay with half-lives of sometimes billions of years, and that allows these atoms to act as an atomic clock, enabling rocks that they're encrusted within to be dated. So that's basically, very simplistically, how we date things going back such long periods of time. And the first indication, possible indication of life, is in rocks that are 3.8 billion years old, and it's based on just the isotope ratio C13, C12 in carbon-bearing material within those rocks, which is lighter in living things than it is in a natural environment, because life prefers, it's a kinetic process, and life prefers the lighter element. So the fact that this lower ratio was found could be suggestive of a biological source. But this is very indirect, and not everyone is convinced that that's the case. And we have to go forward another 300 million years to about 3.5 billion years ago to get definitive evidence for life, which are these fossil stromatolites, and a picture is shown there. Stromatolites are these rocks with a layered structure, basically layers of fossil cyanobacteria and sediment. And the belief in this is strengthened by the similarity of these fossil stromatolites to living stromatolites, which are still out there. You can see a picture of some of these in Western Australia, I think this picture is from. So we have definitive, very concrete evidence for life going back 3.5 billion years. One can actually see through electron microscopy images, pictures of fossil cyanobacteria. Here are a couple in old rocks. And so we can see the morphology, which amazingly is not that different to the morphology of living cyanobacteria. So cyanobacteria have at least shown that they know how to stick around. And again, that's significant, and we'll talk about that, more about that as we go along. Where? What location on the early Earth did life appear? Isn't that an interesting question? Wouldn't we love to know? Well, the first person to make some proposal about that was Charles Darwin, the great Charles Darwin, who the fact that he had this suggestion so early in the piece, when so little was still known, is just extraordinary. Just showed his amazing intuition. He talked about a warm little pond with ammonia and phosphoric salts and energy, light, heat, electricity. Wow, that was really forward thinking. Sorry?
Preceding the Urey experiment.
I'm sorry?
Preceding the Miller-Urey experiment.
Well, by quite a bit. And then, of course, a little later, in the early 20s, two scientists, J.B.S. Haldane and Alexander Oparin, said this a little bit more formally. They called it a primordial soup, but they spoke about a process of chemical evolution. In other words, there was a process that the chemical stuff evolved in the direction towards life. And that was another step in the direction of thinking about where it might have happened in some primordial soup. In the 60s, quite a wild proposal was put forward by a chemist called Graham Ken Smith, and he proposed that life began on clay surfaces, and it actually began with replication on a mineral lattice. It wasn't organic at all, and at some point that replication process was taken over by organics. That was, again, highly speculative, but there was interest, I guess, in the idea, because what you learn once you deal with the origin of life problem, and we'll see this subsequently, you have to think out of the box. If you think conventionally, you don't get very far. This was certainly out of the box, and we don't really believe it today. There's no support for that idea, but it was a different way of thinking about the problem. So for historical interest, I mention it. The popular proposal for the origin of life today would be the hydrothermal vents hypothesis, basically volcanoes under the sea, spouting out all of this chemical active materials, hydrogen, H2S, ammonia, carbon monoxide, CH4, and you have also not just chemical energy within those active molecules, but also you have physical energy through ion gradients. And the fact is that around those vents, you have life is teeming, different kinds of life, to, of course, what we know, but it seems that that sort of environment is certainly conducive to life. As I say, this is I would say, the flavor of the month. One can say very popular for the last 10, 20 years. But quite a few people question this and are skeptical. And to show you that origin of life people aren't always very polite, let me show you a comment by a distinguished chemist from Oxford who gave his opinion about this proposal. He said, the idea that life originated at vents should, like the vents themselves, remain in the deep bosom of the ocean buried. That's, he made his opinion very clear. But there are other reasons, or there are reasons for questioning that. I'll mention one in a moment. And the most recent proposal is the hot springs idea from Armin Mulkajanian, who said that the ocean environment is not an appropriate one because protoplasm cells are rich in potassium but poor in sodium, and that's inconsistent with a sea-water origin where the ion concentration exactly the opposite. So I want you to see what amazing advances we've made in trying to figure out where life emerged. Darwin started off with a warm little pond, and we now believe it happened in a hot spring. So 160 years, that's the progress we've made. And now I'll tell you the true answer to the question, and that is we have no idea. And there's a reason for that. And the reason is it's a historic question. And if you want to answer historic questions, you have to have a historic record, and there is no historic record. Because there is no fossil record of pre-life. It doesn't exist. We don't have any evidence for pre-life in fossil form. And therefore, all of these proposals, maybe they're interesting, but they're not falsifiable. And that's a big problem in science, you know that. If a theory isn't falsifiable, one can question its usefulness. And one other way of maybe proving that one of those ideas was right was do it. Create those conditions and show how all of a sudden, I don't want to say creepy crawling things come out of the system, but at least some process moving in the life direction, and that hasn't been done either. So I would sum this part up by saying consideration of origin of life's likely historic location, it's thought-provoking, very interesting, but it ultimately is speculative, we don't know. Now the how question, which I think is the interesting one, coupled with the why question, which will come up subsequently. What chemical path was taken, and this is a chemical problem, that would have led non-life to life, and this is already built on several elements. First of all, where did life's building blocks come from? How could they have come about? Because those molecules I showed you earlier, they're not just lying around all over, they have to be made somehow. And then on the basis, what chemical pathways then could have brought about the formation of these molecules? Now life, very simplistically, one can think of it as a protein nucleic acid system within a lipid membrane. Proteins, that's amino acids, nucleic acids, made of nucleotides joined up. Lipid membranes, of course, are made of lipids. So how could amino acids, nucleotides, lipids have formed naturally? And here we have some reasonably good answers. And basically from simple molecules, such as those you see here, hydrogen, carbon monoxide, ammonia, formaldehyde, hydrogen cyanide, one can get to lipids, amino acids, nucleotides, which can then complexify further into vesicles, peptides, proteins, RNA and DNA. Let's have a look at that in more detail. Lipids. Well, it turns out there's a chemical process, the Fischer-Tropsch synthesis in chemistry, whereby hydrogen and carbon monoxide, under the right conditions, mineral catalysts, conditions that are considered to be, I've put that in unintentionally there, in hydrothermal vents, after I just said some unfriendly things about them. But hydrogen and carbon monoxide can be catalyzed to form hydrocarbons, and amongst them fatty acids with the hydrophilic head and the hydrophobic tail shown here. And of course, once you have that kind of molecule, you can form vesicles through the formation of bilayers. Amino acids, where did they come from? Obviously a very important life entity, because proteins are made of amino acids. And that leads us to one of the great the spectacular reactions or discoveries in prebiotic chemistry, that if you, Stanley Miller in the 1950s, if you take a mixture of simple gases, nitrogen, methane, hydrogen, ammonia, water vapor, and you put a spark through it, almost following Darwin's recipe, amazing. What do you get? Amino acids galore, amazing. Very unanticipated, but it just shows that chemistry, we know a lot of chemistry today, but there's still chemistry that we didn't know and couldn't even have anticipated that just through such molecules one could get interesting molecules like amino acids. And just another interesting thing, when you get a whole lot of amino acids, one has to add in small quantities and in horribly dirty mixtures. It's not as if you get, you know, lots of these amino acids in useful amounts. But when one looks at the distribution or the amounts of the various amino acids from the discharge experiment of Miller and compare it with those in the Murchison meteorite, this big meteorite that fell on Australia in, when was it, the 60s somewhere, or late 50s, don't remember exactly. One sees a remarkable similarity in the relative distribution, which seems to imply that the formation of amino acids in these quantities might be like have a cosmic basis rather than just it was an accidental thing that happened in Miller's experiment. But anyway, that's a little bit speculative. I don't want to go too far with that. But what is clear is that amino acids are materials that can form naturally. Nucleotides. Where do nucleotides come from? Nucleotides are very fancy molecules. They're large molecules and they're made up of, one can say, 3 primary segments. A phosphate group here linked to a sugar, ribose at the 5' position, and then also a nitrogenous base that's connected to the sugar at the 1' position. So where did those molecules come from? And initially we should ask, of course, that molecule, AMP, you probably all heard of ATP, so that's just the cousin of AMP with just 2 phosphate groups less. So this is a very basic molecule in biology. And the nitrogenous bases aren't just the one shown up the top here, adenine, but there are others as well that could be there to make up the different nucleotides that are possible: thymine, cytosine, adenine, and guanine. And so if we want to know where these kind of molecules could have come from, let's ask where would the different components of those molecules have come from. And we'll start off with the phosphate group. Well, that's easy. Phosphate rocks are all over, no big deal. So phosphate is an abundant mineral and one doesn't have to explain where it came from. The next one, sugar. We put it in our tea and coffee, not that particular one, but it's a very important molecule in biology because ribose, of course, is the link that joins up the different nucleotides. Where can a sugar come from? You don't see them lying around. And it turns out quite easily that if you take the simple molecule formaldehyde and react it with base with catalyst, you end up with ribose. And the remarkable thing is this is an ancient reaction from Darwin's time. Butlerov discovered it in 1861, and it's called the Formose reaction. And it basically involves the condensation of one formaldehyde with another one to give a 2-carbon system, and then another formaldehyde comes in, 3-carbon, 4-carbon, down to 5-carbon system. That, believe it or not, is ribose in an open chain form. but of course the chain can close to form a ring, and you get ribose in the form that is more familiar, this one here. So sugars are possible, could have come about under prebiotic conditions. Nitrogenous base, that already seems more complicated. That's already quite a fancy molecule in itself, adenine. Where would molecules like this come from? And it's not just that one, there are a whole bunch of them. The pyrimidines, which uracil, thymine, cytosine, and the purines, the bicyclic systems. The pyrimidines are monocyclic systems. Where would they have come from? And again, sometimes people were working hard to try and explain that, and Jean Aurore, already quite a few years ago, discovered the remarkably simple reaction that if you take cyanide and reflux it in water, you end up with some adenine. Amazing, but that's how it is. Chemistry is very versatile.
What's
so,
refluxing?
sorry?
What's refluxing? Refluxing.
Yeah, refluxing is boiling up, cooking. But chemistry is fancy words. And here, pyrimidine synthesis, again, rather simple. Two basic molecules, cyanoamide adds water to form urea, and cyanoacetylene adds water to form cyanoacetaldehyd, and these two can react together to form cytosine. And if you hydrolyze cytosine and deaminate, remove the nitrogen, you end up with uracil. So again, under conceivable prebiotic conditions, these molecules could come about. So the conclusion here is nitrogenous bases do seem to be prebiotically accessible. Obviously, we have to have access to materials. I just have to keep track of time here. Okay, but then the area ran to a problem that when you try and join ribose to cytosine to make cytidine, a nucleoside, it didn't work. They wouldn't join up. And this remained a problem for some time until John Sutherland, that chemist who's I already mentioned with his comments about hydrothermal vents, came up with nothing less than a brilliant synthesis published in Nature some 10 years ago for making cytidine here. But he said, don't look at cytidine as being made up of a ribose and a cytosine molecule joining up. You can make it by joining up different bits. And that's what he did in a way that only a very fast-sighted chemist could do. This molecule here, glycoaldehyde, reacting with cyanamide to make this 2-amino oxazole, and you're forgiven if you can't see how that in a few steps can be turned into cytidine, excuse me. But of course, John Sutherland could see that and made this very important discovery. So what's the picture with the building blocks? The picture is reasonably positive thanks to work over 60, 70 years. Many of the building blocks have been shown to be prebiotically accessible. One has to say that hasn't solved the problem, well, for several reasons. One has to worry about the fact that you only get these materials in low yields and in sometimes messy mixtures, but nonetheless, they are accessible. And I don't want to claim that all of the issues in prebiotic building blocks have been solved. There are some nucleotides that haven't been synthesized yet, but the feeling is that's not where the problem lies. The problem lies somewhere else, and I want to come to that now. There's a deep paradox in life, a deep paradox with the very phenomenon that if you take all the molecules of life and put them together, it's not alive. A dead cell has all of those molecules, but it's not alive. Life is not just a chemical state, it's a very special organizational state, and we still haven't come to grips with the nature of that organizational state. What is it and how did it come about? And this brings me to the last question, and I think this is the most fundamental one, and I say that as a chemist, a physical organic chemist. Why? What was there a driving force that pushed dead stuff to become living? And I'll try and show you there is, and that within that statement is, if you like, part of the life mystery is there. The physical question, how did that come about? So we have to talk some basic physics. I'm sure some of you can cook. This is not a very challenging thing to do, to take eggs and turn it into an omelette. And I'm sure many of you can do that. But here's a more challenging thing that I think very few of you know how to do, and that is how to turn an omelette into eggs. And the reason for that is, one direction is the thermodynamic direction. That's downhill, if you like, thermodynamically, whereas the other one is counter-thermodynamic, and therefore it doesn't work. When we talk about going from life's building blocks to this living entity, it's counter-thermodynamic. It's going uphill to something unstable. Going the other way, notice, is very easy. We are all good. We're good at turning living things into dead things. That's quite easy. Just take that thing, pull it apart, and you've got your building blocks. That's called death, by the way, that process. It has a name. But of course, the counter-thermodynamic path, that's the big challenge. How did that happen? So the question that often is asked, how did life emerge, I think should be asked differently. How could life have emerged when the laws of physics say it shouldn't have emerged? And when I say that, I'm not just quoting myself here, but some of the top physicists of the leading physicists of the last century found the question of life as a phenomenon that it just didn't make sense. They said it a little bit more elegantly, but let's say Karl Popper, the famous philosopher of science, an impenetrable barrier to science and a residue to all attempts to reduce biology to chemistry and physics. Erwin Schrödinger, there are undiscovered laws of nature. Basically, what they were saying in bluntest terms, that to a physicist, biology does not make sense. And that is the problem, that biology somehow hasn't been able to connect to physics and chemistry, and it must, because there's nothing in a biological system other than molecules, and therefore there has to be a connection, and the challenge is to find that connection between physics, chemistry on the one hand, and biology. Just something about the probabilities. I mentioned before the probability of life coming together spontaneously was this big number. I just want to show you how big that number is by this little mental exercise, that if, you know, we'll be talking, I'll mention a little further along RNA. And RNA is, of course, this molecule made up of 4 different nucleotides. And if you have an RNA of length 100 nucleotides, the number of possible RNAs, 100 units long, would be 4 to the power 100, because each position has 4 possibilities, 100 positions, 4 to the power of 100, which is 10 to the power 60. So if one of those has a catalytic property that's valuable as opposed to the others, and we want to find that, and we want to synthesize all of the possibilities, it will take some time because there are a lot there, 10 to the 60th. And if I'll tell you, I'm going to be very liberal with the amount of time I'll give you. I'll give you a billion years. That's very liberal. If you want to do that in a billion years, then you have to make 40 times the weight of the Earth of one molecule of ribozymes of these RNAs every single day. In other words, you have to make that much RNA every day for 1 billion years to get through all of the possibilities. Okay? So what I'm trying to say here is 10 to the 60th is a very big number. If 10 to the 60th is a very big number, what would you call this? I mean, you just don't even want to think about it, you know, it just might overload the brain. Okay, so the point is, life could not have come about in a spontaneous, arbitrary, that's the message here, process. It was directed, and we have to find what directed it. Okay, so let's tackle this in a totally different way and look at this scheme that I've shown here. Traditionally, we think about the origin of life in this way. Non-life goes through some mysterious chemical phase to make simple life, and then the biological phase kicks in, Darwinian evolution, broadly speaking, very broadly speaking. Lots of arguments about Darwinian evolution, but that's not important now. And we get to complex life. Can the chemical and biological evolutionary pathways, processes, be related? And there's this new area of chemistry, very new area of chemistry, systems chemistry, that attempts to do just that. The term is new, it was only coined in 2006, and it's a play on words. Systems biology, you've all probably heard of. It's a top-down approach to understanding biological systems. Here, we're doing it bottoms up, starting with basic molecules and the essence of systems chemistry, and different systems chemists might view this somewhat differently, but my take on it is it deals with simple replicating chemical systems and the networks that they establish. And something very important in all of that is replication is a very important reaction, a very special reaction for reasons that I will show you in a moment. So what does this systems chemistry do? Regular chemistry deals with non-replicative systems, A being transformed into B or C, reactions. Biology ultimately is complex replicative about complex replicative systems. All living things replicate, or have to be careful in how I say that, but replication is certainly central within biology. And systems chemistry is an attempt to bridge between these two worlds by looking at simple replicative systems and thereby connecting regular chemistry to biology. So, what does systems chemistry, taking that sort of approach, tell us about the origin of life? That the beginning was some replicating entity. Don't ask me what it was, because that's a historical question and I don't have the answer, and it's not that important in a sense. There was something there, and then once you had that replicating entity, there was one physical chemical process that led from that entity towards life. And something very important, and what drove that process? The drive towards greater stability. But to understand that statement, we have to talk now about this word here, stability. Stability is a complicated word, and there are different kinds of stability, and that's what we have to clarify now to allow that statement I've made there to make sense. But the point here is that the process of emergence, we say, had an identifiable driving force, and now what I want to try and do is to identify that driving force. Some stabilities, a few words. This is a 2-minute course on thermodynamics. Thermodynamic stability, you're probably all familiar with that, associated with the system's energy. Central to that is the second law of thermodynamics. And you all know that if you have a gas in a cylinder connected to an empty cylinder and you open the tap, the gas will go from being in one, it'll spread over the two, and you've gone from an unstable state to a stable state. What this remarkable man, Ludwig Boltzmann, said towards the end of the 19th century, that the reason that happens is we're going from a low probability state to a high probability state, and came up with his famous entropy equation. Basically, just in simple terms, the reason that this state is more stable than that one is that it's more probable in the sense that there are more ways of distributing all of those molecules over two cylinders than within one cylinder. You can play around, if you just do it with 4 balls instead of with billions of it, it's very easy to show that. But the point is that this doesn't just apply to physical systems, it applies to chemical systems as well. So if I take the reaction of hydrogen and oxygen, which reacts to make water, water is more stable thermodynamically than hydrogen and oxygen. But the reason is because there are more microstates that describe, the equilibrium is to the right, because there are many more microstates that describe water than there are microstates that describe hydrogen and oxygen. So the principle is the same, even though here it's for a chemical process. But there are there's not just thermodynamic stability out there that we have to deal with, there's other stabilities, and when I say other stabilities, I'm talking about kinetic stability, which is stability in terms of time and not energy. So kinetically stable systems are unstable thermodynamically, but they're still stable. Not stable in thermodynamic terms, but stable in the sense that they stick around. They're stable in terms of time. So, for example, if you take hydrogen and oxygen and you mix them together, and there is no spark and no catalyst, it'll sit around for 1 million years. It won't react, even though it's unstable. It's kinetically unstable, and this simple reaction graph shows that the hydrogen and oxygen are over here, water is over there, but if the barrier is too high, the molecules can't get over, and you have a kinetically stable system. That's very well known. Anyone who's done a course in organic chemistry, well, not just organic chemistry, chemical reaction theory, very basic, knows about kinetic stability. And just this last sentence here, the stability is reflected in the system's persistence. Remember that word, persistence, because it's very important. But it turns out, and this is the new thing, that there are 2 kinds of kinetic stability. The one I just mentioned, very well known, it's in all of the textbooks, and that's the static kinetic stability, but there's a dynamic kinetic stability associated with certain replicating systems. And we've given this the name of dynamic kinetic stability. We've been discussing this for a number of years now. And the idea is that something can be persistent because it's good at making more of itself. Remember those cyanobacteria that have been around for several billion years? That's already a hint to where we're headed. So, the whole story starts with replication. So let's start with the simplest replication we can think of, molecular replication. There are certain molecules that are able to make copies of themselves, and not surprisingly, we call these replicating molecules. And an example of that are RNA and DNA, long sequential molecules with building blocks. And this kind of molecule, if you take RNA, mix it with its activated building blocks, you end up with lots of copies of RNA. And initially that might sound mysterious. How could that happen? The mechanism is actually quite trivial. The RNA, the initial RNA molecule acts as a template to all the building blocks. You may know this from how DNA, of course, replicates. And they just fit, the appropriate building block fits into place. Initially, you actually don't get a copy, you get the complementary, if you like, copy of the RNA. But then if the complementary then makes a copy of itself in this template fashion, you end up with the original. So, well understood now, very simple, well, it's not simple, but just to mention the process in general terms is simple. A replicating mechanism based on the template is the way that molecules can make copies of themselves. But, so this is just another chemical reaction. There are millions of chemical reactions. So you've shown me another one called replication. What's the big deal? It is a big deal because it's autocatalytic and it can exhibit exponential growth, and that is very important. If you start off with one replicating molecule and it replicates 79 times, you end up with a mole, the Avogadro number, because 2 to the power 79 is the Avogadro number. And in principle, if you were to do another further 83 cycles of replication, you would end up with a mass equal to that of the Earth. So what I'm saying is exponential growth goes crazy very quickly, and that's the power of autocatalysis. That's not very novel, actually. Someone called Thomas Malthus understood the power of kinetic power of replication, exponential growth, a long time ago in his essay on the principle of population, 1798. But the implications of that on chemical reactivity have not been adequately appreciated, and I'll now try and show you a little bit on that, because that power of replication changes chemistry. It leads to a different kind of chemistry, which in brackets we call biology. Let me just show you in an illustrative way just the kinetic power of replication. Think of catalysis. You have A plus B plus C, and I have one molecule of catalyst X, and it makes Y. Every time that an A, B, and C to come together, thanks to X, you end up with a Y. And this is a very efficient catalyst because it makes 10 to the 6th molecules of Y every second. So that is, efficient, right? How long would it take to make a mole of Y? Well, the answer is, because we only have one molecule of catalyst, that's the tricky bit. The answer is 6 by 10 to the 23rd divided by 10 to the 6th, or multiplied by 10 to the minus 6, it's the same thing. It leads to 6 by 10 to the 17 seconds, which is 20 billion years, longer than the lifetime of the universe. So if you just have one molecule of catalyst, catalysis, 20 billion years. Now let's do the same exercise with autocatalysis, where X doesn't make Y, but it makes another X. Now it's going to be faster because you're making more catalyst all the time. So it's not going to take 20 billion years. Does someone want to estimate how long it'll take to make a mole of X with autocatalysis? Someone, yeah? Make a guess. 1 billion years? 1 million years? No one? Sorry? A day? A day? Anyone prepared to take that? Sorry? 1,000 years? Okay. The answer? 79 microseconds. Instead of 20 billion years, 79 microseconds. Why is that? Because each replication is a microsecond, 10 to the minus 6 seconds. We're doing 79 replications. 79 times 10 to the minus 6 is that, 79 microseconds. That example is a little bit artificial because I've done it starting with one molecule, which is not a realistic example, but it does illustrate the profound power of autocatalysis versus catalysis. Catalysis, 20 billion years versus 79 microseconds, a 10,000th of a second. That is amazing. And here is hidden life's secret. Eventually we'll see that. So autocatalysis is an extreme expression of kinetic control. Replication is unsustainable. That's the clear conclusion. And therefore, if a replicative system is stable, it has to be stable in a way that the rate of replication, the rate of replicator formation, and the rate of decay are roughly in balance. And what does that mean? A system of this kind where you have the building blocks coming together to form the replicating system, which then undergoes decay back to the building blocks, and you just maintain this dynamic system over time. And that way you can achieve stability through formation and decay. And that can be demonstrated with a very simple differential equation. I don't want to spend too much time on it. It's trivial: rate of formation, rate of decay, and when you have dx dt equals 0, that's just a steady state population of replicators. And here is a very simple physical metaphor which kind of illustrates the idea. That's the fountain in Geneva, and it's stable in the sense of persistent, because whenever you go to Geneva, it's there doing what fountains do, you know, fountaining. I don't know if that's a word. But the water that makes up that fountain is turning over all the time. It's not the same water in the fountain, okay? The fountain is stable, but the water is turning over all the time. In the same way, if you have a replicating population, the population is stable, but the entities that make up that replicating population are turning over all the time. So the replicating system stability, and it's this kinetic stability, is of a dynamic kinetic kind as opposed to the static one that I mentioned earlier with hydrogen and oxygen, which is well known. So, and if we now characterize that state, the dynamic kinetically stable state, it is based on irreversible replication, because otherwise, if it's not irreversible, don't have time to go into this in detail, but you won't get the exponential growth. And it's dynamic, and I've explained that. It's non-equilibrium. This is not an equilibrium state. It's a steady state, and the proof of that is that it has to be energy fueled. If you turn off the pump on that fountain, there's no fountain, it stops, okay? So in the same way with the replicating system, if you don't have a continual source of energy, the replicating population will just stop. It doesn't keep going of its own accord. It's not an equilibrium, it's an energy-fueled steady state. Okay, what's the big deal? Why is that important? And here comes the central idea here, which is very important. That once you have replicators in a DKS state, they can evolve. You can have a process of evolution. Why is that? Because remember that differential equation that describes the steady state for a replicator x1, let's say. But if x1 somehow replicates imperfectly, a mutation, and you end up with another replicator instead, x2, what happens when you have x1 and x2 competing for the building blocks to replicate? And when you solve those two differential equations together, the result is, and it's a very trivial exercise in kinetics, that one of the replicators just disappears, goes to 0, and the other replicator reaches its steady state without that first replicator. In other words, once you have a replicator mutating and forming another replicator, the one that is better, the better replicator, will drive the other replicator into extinction. And this was shown some years ago by leading people in the area. The kinetically, and the conclusion here is the kinetically more stable replicator drives the kinetically less stable one into extinction, and the result is evolution. Persistent replicators will tend to evolve towards greater stability, but this other kind of stability, this dynamic kinetic stability that I mentioned earlier. And I told you about a great, the great experiment in prebiotic chemistry of Stanley Miller. This is the other great experiment in prebiotic chemistry. Great experiment done by Sol Spiegelman, 1967. I mentioned that if you take RNA and you give it building blocks, it makes copies of itself, right? Just a replicating molecule. But sometimes the replication is not perfect. It makes mistakes, and you get an imperfect copy. What he did was, he went through 74 cycles of replication of a particular RNA with 4,500 bases, building blocks, if you like, and he ended up with a mutant that was just 220 bases long. the RNA started to shorten. And why was that? Because shorter RNAs replicate faster than the longer ones, and you just have this competitive system where faster ones were outcompeting the slower ones, and you got this sequence of events. Look at it: replication, variation, selection, evolution. That sounds suspiciously like biology, right? But here we're no biology, we're talking molecules, just molecules. We're starting to see biological behavior at the chemical level with replicating molecules that show that Darwinian type process. So we see evolution takes place at the chemical level, and now I'm going to go back to my early scheme. Remember I said if we start off with a replicating entity, chemical phase to simple life, biological phase, Darwinian evolution to complex life. Now we see having a replicating entity is not enough. It's got to be in that decay state in order for that evolutionary process to kick in. And now we can specify what the driving force is for that process. It's the drive towards greater stability. But this dynamic kinetic stability, this other kind of stability, not static kinetic stability and not thermodynamic stability, but it's stability nonetheless. Stability as persistence.